Hello, how you doing?
Hi, how are you, Miss Bennett?
I'm doing good. How are you?
Good, good.
That's good.
In a minute, we'll begin. So Ania have joined us. So I think we can start. Today we continue like before from where we stopped. I think I opened a lot of pages, so I'm gonna close some of them. Yeah, I'm gonna close this. Okay. So today we'll be starting at discussing more concepts and probability. Excuse me. So some of those concepts we'll be looking at include what we called, the first one would be mutual exclusiveness. Then dependent events. Dependent events. Dependent events. Independent events. Events. Addition rule. And a multiplication rule. So if time permits, we can also look at conditional probability. Okay, let's start. First one. Let's start with mutual exclusiveness. Two events are mutually exclusive when the occurrence of one event or when the two events cannot happen at the same time. See? For example, one cannot be a Democrat and a Republican at the same time. You are either a Democrat or you're a Republican. Now, when a card is drawn, one card, you cannot get a card that have both 4 and 6 number on them. It's either the card has a 4 or a 6. So when event happens, it prevents the other one from happening. So also getting a king and an ace at the same time, not possible. So mutual exclusiveness means that when one event happens, the other one cannot happen at the same time. So next one is the dependent event. Two events are dependent if the occurrence of one event affects the other event in such a way that the probability of their joint occurrence changes. For example, if you look at these two events, getting good grades and getting a scholarship. The event getting good grade happens, if it happens, then the event getting a scholarship might happen. So event A affects event B in a way that the probability of their joint occurrence changes. How about this one? When you park in a no parking zone, that's an event. Then you get a parking ticket. That's another event. So this one, parking in a no parking zone, affects the other one, which means getting a parking ticket. Now, another one is this: drawing a card from a deck and not putting it back, then draw another card. Before you make the drawing, the draw, there are 52 cards. After you pick a card, they are now have 51 cards left. So if you don't put it back to draw this before you draw the second card, and if you get the probability, it will change. So these are the independent events. Now, independent events are those events where the occurrence of one event did not in any way affect the occurrence of the other event. For example, if you win a lottery in Maryland, that does not mean that you win if you win a million lottery jackpot, that doesn't mean that you're gonna win a New York lottery. It's totally independent. Or drawing a card and getting a queen, then replacing it, then drawing another card and getting a queen. Again, they are totally independent. So for this concept, there are rules for those concepts that I just explained. So there's a place I wrote those rules down. Let me take you there. Okay. Excuse me. So for the addition rule for mutually exclusive events and the rest of the rules, you can see them here. Okay. So for mutually exclusive event, say the additional rule, let's say that two events A and B are mutually exclusive. So according to the additional rule for this, it means that probability of A or B occurring equals probability of A occurring plus probability of B occurring. But if there are up to three events, so probability of A or B or C equals probability of A plus P of B plus P of C. Now, how do you know that we're going to use plus here? The key word is all. It is all. That means you're going to use addition rule plus. See? You see that they are all B or B or C. Now, if the events are not mutually exclusive, there'll be a slight change. In that case, the probability of A or B is probability of A plus probability of B minus the probability of A and B. This is for non-mutually exclusive events. Actually, you can use this one for both. Because for mutually exclusive event, this part of the formula turns to 0. See? So usually I recommend that my students use this one for both mutually exclusive and not mutually exclusive event, because sometimes you might see a question, you might not be some students might not be able to determine whether the information from this question shows if they are mutually exclusive or not. So in that way, if you use this one, if the events are mutually exclusive, as we are doing the calculation, this part will automatically change to 0 without you doing anything about it. So that means that this can be used for either or. But if you have the ability to identify which events are mutually exclusive at any time, in that case, use this for mutually exclusive event and use this one for non-mutually exclusive event. But at the same time, either way, remember that the keyword is or. That tells you you're going to use additional rule. Sometimes there may be 3 events. In that case, the probability formula will not become P of A or B or C, which is P of A plus P of B, where P represents the probability, of course, plus P of C minus P of A and B minus P of A and C minus P of B and C, then plus P of A and B and C. This is when there are 3 events, Now, for multiplication rules, the keyword is and. Once it's and, if the question asks find the probability of A and B, that means you know that you're gonna use the multiplication rules. For independent events, it is probability of A and B is equals P of A times P of B. And for 3 events, it's gonna be P of A times P of B times P of C. Sorry, P of A and B and C. That means P of A times P of B times P of C. Now, when the events are with two events are independent, this is just occurrence. You can say so. Probability of B given A. This is where when we start doing the conditional probability, we can start using this one, part of this for this, because this one, the slash here means given. So we return to this one later on. Now, all these formulas, when we say them, they become like monsters. But when we start using them, you see that they are actually easy to use. So this part is usually for dependent events, even though this part is kind of give a condition. Like here, for dependent events, we use these formulas for the multiplication rule for dependent events. This is read as follows. Probability of event A and B, and is the keyword here. That will tell you that you're going to multiply. Is the probability of A will occur times the probability that B will occur, given that A have already occurred. I'll give you an example. If A is getting a scholarship, sorry, if A is having good grades and B is getting a scholarship, so the probability of A and B occurring becomes the probability that you have good grades, which is A, times the probability that you have a scholarship, given that you already have good grades. Now, enough of the formulas. Let's start using them. You will see that they are really not bad. Okay, so I'll take you back to where we start using these formulas. Okay. The first one we try is this one, number 13, then 14 and 15, to give you a background. It says, 13 says, at a political rally, it says, there are 20 Republicans, 13 Democrats, and 6 independents. If a person is selected at random, find the probability that he or she is either a Democrat or a Republican. You can see the or right there. See the or. So in that case, you're gonna use the addition rule. So the probability that, let us use D for Democrats. D for Democrats. Yeah. Then you have R for Republicans. Excuse me. And I for independents. So now, according to the information we have, there are 20 Republicans. So you have Republicans, 20 of them, R equals 20. Democrats have 13. Independents has 6 independents. So that our sample space is total will be, I will add all of them. Let me get my paper. Put this down. We're add 20 plus 13 plus 6. So we can add them up using our decimals. We got 20 plus 13 plus 6 at 9. So we got 39 here. Okay, 39. Now, the question says, if a person is selected at random, find the probability that he or she is either a Democrat or an independent. In each case, you must get your total first. Okay. So we have because it's a probability of Democrats or independents equals probability of Democrats. This is what the addition rule says. Give me 1 minute. Plus probability of independents minus probability of Democrats and independents. Now you will see why I said that this part will turn to 0. Yeah, equals Democrats. We have how many of them? 13 out of 39. Okay, plus Republicans. How many of them? 20. Sorry, when we don't need Republican, we're looking for Democrat or Independent. So Independent are 6 out of 39. 6 out of 39. Okay, minus Democrat and Independent. You can't have that. Nobody can be a Democrat and Independent at the same time. So the answer becomes 0 over 39. So you can see why I said when we are looking at the formulas to use this formula for either for mutually exclusive event or non-mutually exclusive events, because they'll give you the same results. So putting this in the calculator will give us the answer we are looking for. We have 13 over 39 plus 6 over 39 or 0 over 39. 0 over 39, we know that it's 0 already. So I'm going to put this on in a calculator so we can see the results. So we have, okay, 11 divided by 39. Okay, plus 6 over 39. 39. Okay. Minus, of course, 0 over 39. You know that it's already 0, but I'm gonna put it here just to fulfill the formula. 39. 0.435897. So we just tried the third decimal place. 0.436. Okay. 0.436. Or you can call it 43.6%. Any question on this?
No.
Okay, good. So sometimes they might ask the question in a different way. Maybe they use a chart like this one. It says, like this question says, sorry about, I'm just a little bit slow today. Anyway, so this is the question we have here. It says, the 985 pedestrian deaths that were caused by accidents are shown here. It says, driver intoxicated, pedestrian intoxicated. So if one pedestrian death is taken at random, okay, so 1 minute, I'm gonna fix this. So if one pedestrian death is randomly selected, find the probability that the pedestrian was intoxicated or the driver was intoxicated. Okay. In this case, we can use this, have solution. So we get the totals for this and totals for that. So we're gonna find this here. Okay. So I have totals already for these two. I'm gonna put them in so we can get our probability. I'm gonna add this total here. Okay. So I'm gonna draw it out. Totals. So if you add this to 59 plus 79, I got 138. Then if you add 266 plus 581, I got 847. And then for here, I got the same total. Do the same thing, totals. This one has, if you add this two, you got 325. Add these two, you're gonna get 660. Then if you add all of this, either these two or that two, that will give us 985. Now we're ready to answer this question. It says, if one pedestrian death is randomly selected, find the probability that the pedestrian was intoxicated or the driver was intoxicated. So let us use the P for pedestrian here, then D for driver. So it says here, A part says, find the probability. If one pedestrian death is randomly selected, find the probability that the pedestrian was intoxicated or the driver was intoxicated. In that case, all you have to do is, because of this keyword or, you're going to use the addition rule. Sorry, yeah, okay, this right here. So the probability that the pedestrian or the driver was intoxicated will be probability that the pedestrian was intoxicated plus probability that the driver was intoxicated minus probability that the pedestrian was intoxicated and the driver was intoxicated. See? Now, for the pedestrian was intoxicated, see all the intoxicated pedestrians here. The yes and no. I mean, all the yes is here. 325 out of the whole 985. So let me put it here. Equals 325 out of the whole of 985. Yeah. Plus, next one is that the driver was intoxicated. This is the section for driver, the rules. Driver intoxicated. See, yes, you have 138 out of the whole of 985 drivers and pedestrians. So 138 out of 987. I don't 985, yeah, 985. Then minus pedestrian was intoxicated and driver was intoxicated. See, the pedestrian was intoxicated. Yes, all the yeses on this side. Then driver was intoxicated, all the yeses on this side. They intersect at this point. This is where the yeses intersected. Here, 59. 59 over 985. That will give us the result we are looking for. We're going to write it down. And then we have our results. 325 over 985 plus 138 for 985 minus 59 for 985. So we have it in our decimals in this form. Okay, we have 325 divided by 985. Okay, plus 138 divided by 985. Then minus 59 divided by 985. That gives us 0.410, 4101522. So we stop at the third decimal place, which is 0.410, which is 0.410. 0.410. So that is basically what it is. So for the pedestrian is if this here it says if one pedestrian death is randomly selected, find the probability that the pedestrian was intoxicated or the driver was not intoxicated. In this case, you have B parts. Pedestrian was intoxicated. Pedestrian was intoxicated, or the driver was not. Not is the complement of intoxicated. Driver intoxicated is the event. Driver not intoxicated is the complement. If you remember with the complement we did on Friday. So driver not intoxicated is represented by the complement. So I'm gonna make it like a complement. Okay. So it would be probability of pedestrian was intoxicated plus probability of driver was not intoxicated. Okay, which would be a form of complement. Then minus probability of the pedestrian was intoxicated. Okay, and the driver was not intoxicated. Okay, so now we can plug it in our numbers. Get equals the pedestrian was intoxicated. You can see right here. Yes, 325 out of 985. Okay, 325 out of 985 plus the driver was not intoxicated. That is driver intoxicated, no. You can see right here. See no side. 847 for 985. 847 for 985. Then minus the pedestrian was intoxicated and the driver was not. Pedestrian was intoxicated is right here. Yes. Driver was not. See no here. So you're gonna be they intersect at this point. The yes and no intersected at this point, which is 266. 266 over 985. And we'll put this in the our decimals. Let me write it down. 325 for 985 plus 847 for 985 minus 266 for 985. So I'm gonna put it right there. I'm taking you to decimals so we can put these numbers in. We already have them this part in 25 of 985. We're just gonna change this to 847 over 985 minus 266. 266. So you're gonna have 0.91979. You know, it kept going. So we at the third decimal place. It's 0.920 if you round it up. 920. So that means 0.920. 0.920, or I can call it 92%. Okay, 920, or I can call it 92%. See? Now, questions on this? Any questions?
No.
No questions.
Good. So now that means we can proceed. Next thing we're looking at the multiplication rules. I have already explained it examples. The rules. But now let us use these rules. Let's start with the multiplication rule for independent events. Okay. Then we can proceed from there. So let's look at a few examples on that. It says first one says a card is drawn from the deck and then replaced. So they put it was 52 cards. They take one out. It was 51. They put it back before they make the next selection. See, so when they put it back, it is still the same 52 cards. So it is replaced, then a second card is drawn. Find the probability that of getting a queen and then an ace. So solution, yeah. So let's say that Q equals queen and A equals ace. So, and of course, you know that for the cards, there are 52 of them. So probability of a queen and ace equals, see, the keyword here is and. That's how you know, see the and. That's how you know that it's going to be a multiplication rule. Probability of queen times probability of ace. Now, since this card was replaced, see, it was 52 cards. Then they picked one, get a queen, and replace it before they pick the second card. So that means it is still 52 cards. So how many? Let's find how many aces we have. I think we have a card here. We have a yep, we have ace, 4 aces. 1, 2, 3, 4, and 4 queens. 1, 2, 3, 4. So that means that before they made the selection, there are 4 queens. So that means 4 out of 52 cards. Queen times for ace, there are also 4 aces. So because they put it back, you still have 4 aces left and still 51 cards. Yeah, 52 cards. I'll give us I'm gonna do it on the decimal so you can see. 4 over 52. 4 over 52 cards. That's one mistake. Times, okay, 4 by 52. Okay, so you got 0.0059. 0.0059. 0.0059. See, that is basically what it is. Now I want to do one that involves some percentages. Because sometimes when they include percentages, some students get confused. Now it says Harris polls found that 46% of Americans say they suffer great stress at least once a week. Now it says if 3 people are selected at random, find the probability that all 3 will say they suffer great stress. Yeah, now we are using percent. Like I told you, probability can also be written as a percent or decimal. As you can see from the examples I did, I usually give answers. Sometimes I put the percent value, either way. But let's do the one that's the question that involves where they give you the question in percent form. Solution. In that case, let's say that we use S means stress, great stress. Okay. So we're looking for the problem that say that 3 people are chosen at random. So find the probability that they say they suffer that we say they will suffer great stress at least once a week. So we're looking at the probability that the first person, S1, and second person, S2, and third person, S3, say that they suffer great stress. Equal, yeah. And okay. So is the probability of S1 times probability of S2 times probability of S3. See? So you have to multiply its number of people based on the number of people that are selected. Now, they were told you that this stress has a probability of 46%, which is the same as 0.46. Okay. So what does this tell us? It tells us that since we already have the probability given that that there's 40% of them say that they suffer great stress already. So all we have to do is to add the probability of S1, multiply them probabilities. It means 0.46 times 0.46 times 0.46. And that will give us the answer we're looking for. So we have 0.46. Oh, excuse me. Okay, this is decimals. I wonder why it's not showing. Okay, here to decimals. Okay. Can you see decimals now? Hello, class. Hello.
Sorry, my mic was muted. Yep.
Can you see this? Okay, 0.46 times 0.46 times 0.46. Okay, 0.0973. 0.0973. That's really the answer. 0.0973. Okay. 0.0973. Or if you like, you can call it 9.73%. 9.73%. Yeah. Now, questions?
No.
Let's try one of them for independent events. I mean, for dependent events, when one event depends on the other event. Let's maybe one example we do. You can practice as many examples as you can in your textbook. So, solution. In this case, it says a person has 30 CDs, of which 5 are country music. If two CDs are selected at random, find the probability that both are country music. Okay, let us use C for country music. I'm gonna make this big. Okay. Country music. Say country music. Okay. Music. Now, he said he has a collection of 30 CDs, of which 5 are country music. If 2 CDs are selected at random, find the probability that both are country music. So it didn't tell us whether they are replaced after the selection before the next selection is made. He didn't say that. We didn't know. So we assume that they did not replace it before they make the next selection. So the probability that the first CD, C1, is a country music, and the second CD, C2, is also a country music, is equal to the probability of the first CD. P of the first CD is a country music, times probability that the second CD, C2, is a country music, given that the first one is already a country music. See? You can see the difference. The independent event one is you just multiply the P's, or you multiply this. But for this one, you have to factor in that fact that because he didn't tell us whether it replaced the first selection before he made the second selection. That means the sample space have decreased. So now, let me explain more on what I mean by that. Before he made the first selection, there were 5 country music. 5 out of 30 CDs. Made the first selection. Times. Now, he didn't replace it. Now, there are now 4 country music left out of now 29 CDs because he didn't replace the first selection. So the probability that the second selection will also be a country music will become 4 over 29. Sorry, over 29. Because he didn't replace the first one, which means that there's now 4 country music left and a total of 29 CDs now instead of 30, because the first one was not replaced. So that will give you a hint on how to figure this out. Let me write it down. 5 over 30 times 4 over 29. That will give us the required probability. Okay. 5 over 30. We got 5 over 30. Okay. Times we have 4 over 29. So 0.02298. So if you round it up, 0.023, call it 0.023, 0.023, 0.023. Questions on this?
No.
No question.
Yeah. Now, the conditional probability, we may not be able to deal with it today. Maybe on Wednesday we'll deal with conditional probability. Before we go, let us do one more example on this dependent events with using multiplication rule. Look at this. Maybe we'll do one of these. Yeah, it says 3 cards are drawn from an ordinary deck and not replaced. See, find these probabilities of getting 3 jacks. This will be our last example today. Wednesday we begin conditional probability and then round off. So 3 cards are drawn. So if they're not replaced, find the probability of getting 3 jacks. Okay, getting an ace, a king, and a queen in order, and so on and so forth. So let's look at the first one. The solution first. It says getting 3 jacks. Let us J means jacks. Okay. So the probability that the first one is a jack, and the second one jack, and the third one is a jack. Okay. You can just call it 3 jacks. Okay. Excuse me. Second one is a jack. First one is also a jack. Is probability of getting the first one is a jack. Okay. Times the probability the second one is a jack. Given that the first one is is a jack already. Times probably that the second one, the third one is a jack. Given that the first one and the second one are already jacks. Now, if this formula will confuse you, if you understand the concept, you don't need to write the formula. Just solve it. If the writing it out will confuse you, so long as you understand the concept, what I'm doing. And I'll explain here. For example, equals how many jacks do we have? We have let's see. Yeah, we have okay. We have 4 jacks here. 4 jacks. Okay. So having that in mind, and we were told that the card we are not replaced. So we can figure it out from there. So before this lesson, we have 4 jacks, 4 out of 52 cards. Then it was not replaced. And we are looking for the probability of getting the second card as a jack. Now there are only 3 jacks left out of now 51 cards because the first card was not replaced. Then for the third jack, we have only 2 jacks left. Okay. Out of now 50 cards. Because the first 2 were not replaced. So this will give us the answer we are looking for. Okay. Equals, we put this on the calculator. This will be our last example. So let me put it on the calculator, then we get our answers. We have 4/52 times 3/51 times 2/50. So I'm gonna put it in. Desmos. So we got 4/52 times 3/51 times 2/50. See, very long. See, 1.08099 times 10 to the power -4. This part, this is what confuses some students. When they see the answer like this, they get confused. But there's not really no need for that, because look at this space. It says 10 to the power -4. This -4 means that you're gonna have 4 zeros before you have the real numbers. So this means that you have before you can write 1 and 8, you need to write 4 zeros at the beginning. So you have 0. So 0.000, say 4 zeros, 18. So you can see that how difficult it is to predict that one card will come 3 times. Like those that buy only one number ticket and keep buying the same number over and over. Before it comes to a point where the lottery have all your numbers. Yeah, it takes time, Question before we leave?
No question.
So let me take your attendance. Yeah, I think I got your attendance paper here. Yeah. Okay. Maya is here. Chambers. Bennett. Okay, I think Aaron left. Okay. Yep. I think we're done.
Right. Have a good day.
You too.
Have a good one. Have a good one.
Bye-bye.